Let's look at the conservation momentum for a differential element. Remember, the conservation momentum says the rate of increase of momentum is equal to the net rate of flow of momentum into the control volume plus the net external forces acting on the contents of the control volume. And so if it were a closed system, you wouldn't have this first term here, and this would literally be F equals ma, but because it's an open system, we have to account for the fact that momentum can flow in and out of the system. If you've ever held a garden hose and turned it on, you felt a force. That's that flow of momentum going through the system. Okay, so what's ma look like for our system? Well, we've done this in kinematics. In the x direction, we have rho times du dt plus u du dx plus v du, oops, that was sloppy, du dy plus w du dz. What is that? Well, this is the acceleration. Remember, that's also called the substantial derivative. And if we multiply it by rho, that's kind of like mass, although this is all per volume basis. And that has to equal forces and flows. Okay? And so on the right-hand side, forces we get are the pressure, which looks like dp dx. We have the body force, or the gravity, which is rho g. This has units of force per mass, so we multiply it there. Makes the units work. And lastly, we have the viscous effects, which propagate through for a 3D flow as d squared u dx squared plus d squared u dy squared plus d squared u dz squared. So that's the x direction momentum equation. In the y direction, we're just going to change u's to v's. And so we get rho times dv dt plus u dv dx plus v dv dy plus w dv dz. And that's going to equal minus d pressure dy plus rho g y. Why are there two different g's? Well, in general, this is just a body force. Gravity, of course, only acts in one direction, probably z. It depends on which way we point our coordinate system. But you could have other body forces like electromagnetic forces, which you could capture in any direction you like. And lastly, the viscous effects, d squared v dx squared, d squared v dy squared, d squared v dz squared. And of course, we want to do this in our third dimension, which is the z direction. So we'd get rho times dw dt plus u dw dx plus v dw dy plus w dw dz. And that's going to be equal to the derivative of pressure in the z direction plus rho g z. And we still have viscous forces. So mu d squared w dx squared plus d squared w dy squared d squared w dz squared. So you might be seeing the challenge here. The momentum equations, along with the conservation of mass, are coupled. So this is a fully coupled system of 4 differential equations. They've got transient, they're non-uniform, and everything crazy about diff EQ all at once is thrown into this set of equations. And so, in general, there are very few places of use that we can solve them directly, but these form the basis for things like computational fluids, where we'll actually solve these equations numerically on a grid. Now, that being said, there's still places we can use them, and the next couple videos are going to give you examples of how you can solve these by hand for special situations.